A Reggiane Re.2000 Falco lay on the seabed at about 20 meters, fragile, historic, and at constant risk of structural failure during any lift. The constraint was built into the airframe itself. This was a rare Reggiane Re.2000 Cat, the Catapultable shipboard variant, strengthened around keyframes and attachment points to survive the brutal acceleration of battleship launches. Decades in saltwater, however, meant that reinforcement could not be trusted to behave like intact metal. From the outset, the job was treated as evidence recovery, not fast salvage. Structural preservation came first. The wreck was discovered accidentally in April 2012. During a training exercise off the coast of Portovenere in the Ligurian Sea, Italian Navy mine countermeasure teams detected an unusual metallic return on the seabed. A follow-up dive confirmed the anomaly was a heavily degraded World War II fighter. The aircraft lay at roughly 20 meters of water, a shallow depth that leaves wreckage exposed to surge, oxygen, and constant coastal agitation that accelerates material decay. Once the identity of the aircraft was confirmed, the operational requirements changed. The Italian Air Force recognized the extreme historical rarity of the machine and desired the wreck for immediate museum restoration. However, the military branch lacked the dedicated budget required to mount a complex marine salvage operation. Heavy underwater extractions require specialized surface vessels and lifting equipment. The marine salvage firm Reggiane stepped in to solve this logistical constraint. The company volunteered to perform the entire recovery operation completely free of charge. This agreement shifted the project into a formal archaeological extraction bounded by strict preservation rules. That preservation mandate made the Catapultabile's internal architecture operationally decisive, not just historically interesting. This aircraft had been heavily modified from the standard land-based fighter configuration for battleship launch, where a steam catapult subjects the airframe to massive acceleration forces. To keep the wings from tearing away from the central fuselage, key bulkheads and frames were heavily overbuilt, with thickened structural nodes tying the primary load-bearing sections together. On paper, the skeleton was tougher than a typical lightweight interceptor, but underwater time would decide what still held. This robust catapult design created a deceptive recovery constraint. While the primary structural nodes were originally built to withstand extreme dynamic loads, they had spent decades submerged in a saltwater environment. The surrounding aluminum skin was severely compromised. Assessing the wreck at 65 feet allowed salvage divers ample bottom time to inspect these components. They observed that the thick catapult bulkheads might still hold together, but the connective material between them was brittle. Any uneven lifting force applied to the fuselage would likely tear the heavy reinforced sections away from the weakened airframe. The salvage firm recognized that standard debris clearance methods were entirely inadequate. The operation required a forensic approach to maintain the physical evidence of the aircraft. Italian historical heritage authorities authorized the extraction under the condition that the airframe be preserved intact. This meant the recovery team could not simply wrap straps around the fuselage. The heavy equipment provided by Reggiane had immense lifting capacity, but applying that raw power directly to the Falco would destroy it. The engineering team had to design a recovery sequence that respected the degraded state of the airframe. Every operational decision at the Portovenere site revolved around this mechanical reality. The shallow depth made site access relatively straightforward, but offered no protection from the physical limits of corroded aluminum. The salvage divers mapped the debris field and measured the dimensions of the surviving structure. They established a clear operational boundary around the wreckage. The preservation of the Serie 2 Catapultabile variant required a highly controlled handling plan that would completely isolate the airframe from typical lifting stresses. How did a specially reinforced battleship fighter end up resting entirely undisturbed on the shallow coastal seabed? On April 16, 1943, a 27-year-old pilot faced an irreversible operational threshold over the Ligurian Sea. Marshalo Luigi Guerrieri was flying a Reggiane Re.2000 Cat on a routine profile when the aircraft developed serious engine trouble, reported alongside abnormal fuel consumption. The fighter's nose was dominated by a Piaggio P11 radial engine rated at about 1,000 horsepower on takeoff. When that power plant faltered, the aircraft lost the thrust it needed to reach land, forcing an immediate shift from mission flying to survival. Without engine power, the pilot had zero altitude to trade for distance. Maintaining lift in a reinforced launch airframe requires high forward airspeed. As the speed bled off, Guerrieri was forced to commit to an immediate emergency water landing. He had to quickly assess the wind direction and the wave swells to align the aircraft for a parallel touchdown. Ditching a heavy fighter is an inherently violent maneuver dictated by approach geometry and the forward impact energy. The pilot had to manage the descent rate perfectly to prevent the heavy engine nose from digging into the sea surface. Striking the water at a steep angle would violently flip the aircraft and trap the pilot inside an inverted, flooded cockpit. Guerrieri executed the controlled crash by holding the nose up and letting the tail section strike the water first to dissipate the forward momentum. Survival in a ditching is decided by seconds. In this case, the decisive fact is simply that the fighter stayed afloat long enough to give the pilot an escape window. Guerrieri released the canopy, climbed out, and swam clear before the airframe finally flooded and sank. Any trapped air within the structure was temporary and unreliable, disappearing as seams opened and compartments filled. Once flooding progressed, the aircraft lost buoyancy and settled through the water column until it struck the shallow coastal shelf. The wreck's relatively intact posture on the seabed reflects a controlled emergency water landing followed by a short, steady descent, not a violent breakup at the surface. The pilot survived the impact, but decades in oxygenated salt water would steadily erase the airframe's original strength. Historical archives and physical evidence do not always line up cleanly in forensic aviation recovery. In the Portovenere case, multiple recovery accounts identify the aircraft as Reggiane Re.2000 CAT, military serial MM8281. Some secondary references have mentioned other serials, but the safest way to settle identity is still the metal data plates and stamped components inside the airframe. Preserving those markings is one reason the recovery had to keep the structure as intact as possible. Finding the wreck was an accident of training, but what followed was procedural. Once the contact was logged, the return was treated as an unknown object to be documented, revisited, and verified under discipline. That shift, from interesting sonar return to controlled identification, set the conditions for everything that came next. Once the survey data locked the target coordinates, the operation shifted from remote sensing to direct physical assessment. ROV footage and diver documentation established the first hard truth: time had already done its work. After more than 7 decades submerged in the Mediterranean, the machine was no longer a rigid flying object. It was a fragile archaeological artifact. At roughly 20 meters, the wreck sat in warm, oxygen-rich coastal water, shallow enough to be worked, but exposed enough to keep the chemistry aggressive. In that environment, salt water behaves like a reactive electrolyte, and over 70 years, the electrochemical attack strips aviation aluminum of its mechanical strength from the inside out, breaking down the alloy's microscopic bonds. The engine block and the thick catapult bulkheads could still look solid, but the surrounding skin and connecting structure had degraded into something brittle, chalky, and unforgiving. Divers mapped the damaged node by node, deep pitting at the wing roots, and a radial engine whose concentrated mass threatened to lever the nose down the moment the airframe was disturbed. But the decisive step was not what they could see. It was what the numbers forced them to accept. Shear strength estimates showed the 70-year-old alloy had fallen beyond safe limits, meaning a conventional lift strap would bite into the weakened metal like a wire cutter. Bounding the search box and mapping the debris was only the first phase of the operation. The recovery engineers were presented with a massive mechanical contradiction. They had to preserve the historical evidence locked inside the cockpit to solve the serial number dispute, but the vessel containing that evidence lacked the structural density to withstand an extraction. The survey confirmed that applying any direct tension to the upper fuselage would result in immediate catastrophic failure. With the metal severely weakened by 7 decades of seawater exposure, how could engineers extract it without tearing the fragile fuselage apart? The geometric layout of a submerged aircraft dictates the exact physical limits of any recovery operation. Engineers faced a hard constraint when calculating the lifting points for the Reggiane fuselage. Decades of saltwater metal decay had destroyed the lower load-bearing structures. Applying direct vertical tension to the upper fuselage bulkheads would cause the heavier lower sections to instantly detach and fall back to the seabed. There was only one conclusion. Conventional slings were off the table, and the lift would have to bypass the aluminum altogether. Instead of pulling the aircraft up from the top, the salvage engineers chose to support it from below. After intensive inspections by divers and a wired ROV camera, the team prepared the seabed close to the fuselage and eased the wreck onto a purpose-built flat frame. That frame, not the brittle aluminum, became the lifting interface. When the crane took the weight, it lifted the entire assembly as one unit, avoiding the dangerous tractions that slings or hooks would have imposed on the fragile structure. The engineers had successfully created a stable subsea foundation, but the entire package still had to survive the dangerous journey to the surface. The final procedural step on the seabed involved securing the fragile load for the vertical ascent. The salvage divers utilized wide synthetic straps to securely lash the fuselage to the underlying steel base. These straps were strictly designed to prevent any lateral shifting as the cradle moved through the ocean currents. They were deliberately routed over the strongest remaining structural nodes and tightened just enough to hold the machine firmly in place. This specific routing prevented the straps from applying any compressive crushing force to the highly brittle outer skin. The engineers created a completely unified lifting package that isolated the historical artifact from all external lifting strains. The subsea extraction method successfully bypassed direct slinging and transferred all structural risk directly to the new steel base. The physical safety boundary between the historic aircraft and the lifting apparatus was now fully established. The dive teams cleared the immediate site and signaled the heavy recovery vessel waiting on the surface. The custom cradle was secured safely on the seabed, but could the surface operators transfer the extreme loads without crushing the brittle aluminum during the lift? With the airframe already secured to its subsea cradle, the surface phase was reduced to controlled connection and controlled motion. Instead of hooking anything to wings or fuselage, the crew lowered thick steel cables to the four corners of the platform and held station directly over the coordinates. Commanded from above by Mikko Perry, the pontoon crane vessel Mikko Perry 30 became the fixed point in a lift that could not tolerate improvisation. Mikko Perry's involvement mattered for one reason: it put serious offshore lift capability on the site under a heritage mindset. After Chief Executive Silvio Bartolotti offered the company's resources at no charge, the operation could be run with the vessels, rigging, and discipline normally reserved for high-cost industrial lifts, without treating the fighter like scrap. With that capability in place, the lift became a problem of geometry, timing, and restraint. Executing a traction-free load transfer requires precise geometric alignment between the surface crane and the subsea lifting frame. As the main winch drums began to take up the slack, the cables snapped taut against the corners of the rigid steel base. The upward force was completely isolated from the historical artifact. Zero-tension lifting ensures that the compromised object only experiences the static downward force of gravity against its support base, exactly as it did while resting on the ocean floor. By redirecting all vertical lifting stress through the structural steel of the cradle rather than the object itself, the engineers prevented the fuselage from bowing or snapping under its own weight. Operating a massive pontoon crane vessel in open water introduces a dynamic hazard known as vessel heave. As the ocean swells roll beneath the surface vessel, the crane boom rises and falls with the wave action. This vertical motion translates directly down the lifting cables to the subsea load. If the crane ship pitched aggressively on a wave, the cables could snatch the rigid underwater cradle upward, applying a massive dynamic shock load to the structure. To counter this environmental constraint, the salvage master required a perfectly calm weather window to minimize vessel movement. The crane operator had to carefully synchronize the main winch speed with the natural rhythm of the sea state to maintain constant even tension on all four lifting cables. The crane operator initiated a deliberately slow ascent rate from the seabed. Moving a heavy flat structure through the water column creates severe hydrodynamic drag. If the winch pulled the steel platform upward too quickly, the rushing water would create a localized vacuum effect and violently scour the remaining aluminum skin off the airframe. The recovery team monitored the tension gauges carefully, ensuring the ascent speed remained low enough to allow the water to flow smoothly around the wreck. The physical recovery lift was completed on December 4, 2013. As the massive, heavy salvage vessel hauled the platform out of the Ligurian Sea, the aircraft broke the surface for the first time in 7 decades. Breaking the surface of the sea introduces the most dangerous mechanical phase of any marine salvage operation. While the wreckage was fully submerged, the surrounding water provided substantial buoyancy, artificially reducing the total weight on the crane cables. The moment the aircraft and the heavy steel platform breached the surface, that natural buoyancy vanished instantly. The sudden, massive increase in physical weight placed maximum strain on the lifting rigging. Because the engineers utilized a traction-free load transfer, the transition occurred smoothly. The heavy industrial cranes easily absorbed the added tonnage without shifting the load. The heavy machinery hoisted the dripping wreckage completely clear of the water and swung the platform over to an awaiting Italian Navy barge. The unified lifting package remained tightly secured to the steel cradle throughout the entire transfer process. The airframe successfully broke the surface intact, but what immediate procedural step was required to prevent the atmosphere from rapidly destroying the metal? The immediate step after surfacing was simple: keep it wet. Salt-loaded aluminum can accelerate into rapid corrosion as soon as it begins to dry in open air. So conservation crews limit exposure, keep the structure continuously soaked, and push straight toward controlled desalination and stabilization. Post-recovery, as the aircraft was secured to an Italian Navy barge and taken straight to the Catapult military base under one non-negotiable rule: it could not be allowed to dry. If moisture evaporated, absorbed marine salts would crystallize inside the porous metal, their expansion prying fragile layers apart and accelerating damage in open air. The only safe path was immediate chemical intervention on arrival, before the wreck ever left controlled custody. The team initiated an active desalination process the moment the barge docked. They constructed specialized freshwater holding tanks designed to accommodate the exact dimensions of the surviving fuselage. Total immersion of marine artifacts in these controlled freshwater tanks creates a chemical gradient that draws the heavy chlorides out of the porous metal. By continuously draining and replacing the fresh water, the engineers maintain a constant chloride flushing process. This totally submerged environment extracts the corrosive salts while physically shielding the vulnerable metal from direct contact with atmospheric oxygen. Getting the wreck into the treatment baths demanded the same discipline as the offshore lift. No new bending loads, no sudden shifts. The ground team kept the fuselage strapped to its rigid steel base and moved the entire package as one unit into the tanks, letting the cradle, not the weakened aluminum, carry the handling forces. The active desalination treatment operated continuously over an extended duration. Conservation teams systematically monitored the water chemistry to track the volume of salt actively leaving the aluminum structure. And once the chloride levels dropped to a mathematically stable baseline, the engineers could safely remove the aircraft from the liquid bath without risking sudden atmospheric destruction. The immediate stabilization protocol proved entirely successful. The rigorous flushing process preserved the remaining structural integrity of the fuselage, the central wing roots, and the massive radial engine block. Following chemical stabilization, the Italian Air Force took direct custody of the artifact and began a long-term restoration program for permanent display at the official Military Aviation Museum in Vigna di Valle. The outcome was made possible by one consistent choice: respect the degraded aluminum's limits, prioritize load transfer geometry over speed, and bypass standard marine slinging from the start. It's treated as an archaeological aircraft rather than industrial scrap. The Portovenere wreck now survives as an exceptionally scarce physical record of wartime aerospace manufacturing, one of the very few Reggiane Re.2000 airframes known to exist today.